what if I told you we could build pretty much everything you see around you right from scratch in just the next few minutes? Well, that's exactly what we're going to do. We are going to construct the fundamental building block of all reality, the atom. So, to get started, let me ask you a really direct question. What are you actually made of? I mean, really think about it. Your hand, the device you're watching this on, the air you're breathing. What's the real stuff that makes it all, well, real? The answer, and this might be a little hard to wrap your head around, is that you're made of almost nothing. Seriously. You, me, this entire planet, it's all over 99.9% empty space. Just this strange, fuzzy cloud of probability. Which raises a pretty big question, right? What's stopping you from falling right through the floor? Well, that's our mission for this explainer. We're going to assemble the tiny, tiny particles that somehow come together to create the solid world that we all experience every single day. Okay, so every great construction project has to start with the materials, right? And for the atom, it turns out we only need 3 fundamental particles. Let's meet the team.
So it all comes down to this. In the very center, in this tiny, incredibly dense little ball called the nucleus, you've got the heavyweights, the positive protons and the neutral neutrons. Almost all of the atom's mass is packed right in there. Then, buzzing around them in this huge cloud, you've got the nearly massless negative electrons. They're the ones that create all the volume, that empty space we were just talking about.
All right, now, to build a specific kind of atom, say gold versus oxygen, we need to know how to read its unique blueprint. And that blueprint, it's all in the numbers. Okay, the single most important number you need to know is the atomic number, which we call Z. It's just a simple count of the protons. And this is the key. If an atom has 6 protons, it's carbon. Period. If it has 7, it's nitrogen. That number is like the element's unchangeable unique ID card. Then you've got the mass number, or A. This is just the total count of all the heavy particles, so protons plus neutrons. And this gives us a really handy trick. To figure out how many neutrons there are, you just subtract the atomic number from the mass number. It's just a little bit of atomic math. But here's where it gets really interesting. While that proton number is locked in, the number of neutrons can actually change. This creates different versions of the exact same element. We call these isotopes. Let's just take the simplest example there is, hydrogen. All hydrogen, by definition, has 1 proton. But your standard everyday hydrogen has 0 neutrons. Now, if you add a neutron, you get something called deuterium, or heavy hydrogen. It's still hydrogen, because it's still got that 1 proton, it's just a heavier version of it. Okay, so we've got our particles, we've got our blueprint, but where do the electrons actually go? And let me tell you, the answer to this question led to one of the wildest and most revolutionary shifts in the history of science. For a long, long time, we pictured the atom like a tiny little solar system, with electrons zipping around the nucleus in these neat, predictable paths. But the reality? Well, the reality is so much weirder. It's more like a fuzzy cloud, where the electron's location isn't a specific point at all, but a whole zone of probability. So why the big change? It's because of a fundamental rule of the quantum world called Heisenberg's uncertainty principle. And what it says is you literally cannot know both an electron's precise location and its momentum at the same time. The very act of measuring one messes up the other. So that neat little orbit, it was never possible. Here's a fantastic way to think about it. Trying to pinpoint an electron is kind of like trying to take a perfectly clear photograph of one single mosquito in the middle of a frantic swarm. You just can't do it. All you can get is a blur, a general area where the swarm is. And so, we had to replace the old idea of a fixed orbit with the modern concept of an orbital. An orbital is not a path. It's a 3-dimensional region of space. You could call it a house if you like, where there's a really high chance of finding a particular electron. And just like houses in a city, these orbitals are governed by a really strict set of rules. You can think of them as the zoning laws of the atom, and they're described by 4 quantum numbers. First up is the principal quantum number, n. This one's the easiest. It just tells you the main energy level, or shell. Think of it like the floor number in a building. The higher the number, the further you are from the nucleus and the more energy you have. Second, you've got the secondary quantum number, L. This tells us the shape of that orbital. Is it a simple sphere, what we call an s orbital, or is it a more complex dumbbell shape, what we call a p orbital? This number defines the shape of the electron's house. Third is the magnetic quantum number, ML. This one specifies the orientation of that orbital in space. So, for instance, if you have one of those dumbbell-shaped p orbitals, is it lined up with the x-axis, the y-axis, or the z-axis? And finally, we have the spin quantum number, ms. And you can just think of this as the roommate rule. Each orbital, each room, can hold a maximum of 2 electrons. And if they're gonna share a room, they absolutely must have opposite spins. One is spin up, the other is spin down. No exceptions. So there you have it. We have the rules. Now let's see how they work in the real world. How they allow atoms to assemble themselves and connect with each other to build, well, to build everything. There are 3 core principles for how this whole assembly process works. First, the Aufbau principle says electrons always fill the lowest energy orbitals first. You know, they fill the ground floor before they move up to the penthouse. Next, Hund's rule says electrons prefer to take their own empty orbital before they'll pair up with another one. And finally, the Pauli exclusion principle restates our roommate rule. When they do eventually pair up, they have to have opposite spins. And this is why all those rules we just learned matter so much. The way the electrons fill up those outermost shells completely determines how atoms connect to each other. Sometimes one atom is like a thief and just completely steals an electron from another. That's what we call an ionic bond. Other times, they're more like partners, sharing electrons between them. That's a covalent bond. And this whole system of buying, selling, and sharing electrons is literally the foundation of all of chemistry. Which brings us right back to our very first question, but now with a twist. We've built the atom, and we know it's almost entirely empty space defined by these weird clouds of probability. So the final question is, why can't you just walk through a wall? The answer is the powerful, invisible repulsion between the electron clouds of your atoms and the electron clouds of the wall's atoms. It's an invisible force field born from the very quantum rules we just put together that makes our world feel so wonderfully and thankfully solid.